In the context of software engineering, software quality refers to two related but distinct notions that exist wherever quality is defined in a business context. Software functional quality reflects how well it complies with or conforms to a given design, based on functional requirements or specifications. That attribute can also be described as the fitness for purpose of a piece of software or how it compares to competitors in the marketplace as a worthwhile product. Software structural quality refers to how it meets non-functional requirements that support the delivery of the functional requirements, such as robustness or maintainability, the degree to which the software was produced correctly. Structural quality is evaluated through the analysis of the software in its structure, its source code, at the unit level, the technology level and the system level, which is in effect how its architecture adheres to sound principles of software architecture outlined in a paper on the topic by OMG. In contrast, functional quality is typically enforced and measured through software testing. Historically, the structure, classification and terminology of attributes and metrics applicable to software quality management have been derived or extracted from the ISO 9126-3, and the subsequent ISO 25000-2005 quality model, also known as SQUARE. Based on these models, the Consortium for IT Software Quality has defined 5 major desirable structural characteristics needed for a piece of software to provide business value: reliability, efficiency, security, maintainability and size. Software quality measurement quantifies to what extent a software or system rates along each of these 5 dimensions. An aggregated measure of software quality can be computed through a qualitative or a quantitative scoring scheme or a mix of both, and then a weighting system reflecting the priorities. This view of software quality being positioned on a linear continuum is supplemented by the analysis of critical programming errors that under specific circumstances can lead to catastrophic outages or performance degradations that make a given system unsuitable for use regardless of rating. Based on aggregated measurements, such programming errors found at the system level represent up to 90% of production issues, whilst at the unit level, even if far more numerous, programming errors account for less than 10% of production issues. As a consequence, code quality without the context of the whole system, as W. Edwards Deming described it, has limited value. To view, explore, analyze, and communicate software quality measurements, concepts and techniques of information visualization provide visual, interactive means useful, in particular, if several software quality measures have to be related to each other or to components of a software or system. For example, software maps represent a specialized approach that can express and combine information about software development, software quality, and system dynamics. Motivation. A science is as mature as its measurement tools. Measuring software quality is motivated by at least 2 reasons. Risk management. Software failure has caused more than inconvenience. Software errors have caused human fatalities. The causes have ranged from poorly designed user interfaces to direct programming errors. An example of a programming error that led to multiple deaths is discussed in Dr. Levison's paper. This resulted in requirements for the development of some types of software, particularly and historically for software embedded in medical and other devices that regulate critical infrastructures. Engineers who write embedded software, see Java programs stalling for 1/3 of a second to perform garbage collection and update the user interface, and they envision airplanes falling out of the sky. In the United States, within the Federal Aviation Administration, the FAA Aircraft Certification Service provides software programs, policy, guidance and training, focus on software and complex electronic hardware that has an effect on the airborne product. Cost management. As in any other field of engineering, an application with good structural software quality costs less to maintain and is easier to understand and change in response to pressing business needs. Industry data demonstrate that poor application structural quality in core business applications, customer relationship management or large transaction processing systems in financial services, results in cost and schedule overruns and creates waste in the form of rework. Moreover, poor structural quality is strongly correlated with high-impact business disruptions due to corrupted data, application outages, security breaches, and performance problems. However, the distinction between measuring and improving software quality in an embedded system and software quality in business software is becoming somewhat irrelevant. Embedded systems now often include a user interface and their designers are as much concerned with issues affecting usability and user productivity as their counterparts who focus on business applications. The latter are in turn looking at ERP or CRM system as a corporate nervous system whose uptime and performance are vital to the well-being of the enterprise. This convergence is most visible in mobile computing. A user who accesses an ERP application on their smartphone is depending on the quality of software across all types of software layers. Both types of software now use multi-layered technology stacks and complex architecture, so software quality analysis and measurement have to be managed in a comprehensive and consistent manner, decoupled from the software's ultimate purpose or use. In both cases, engineers and management need to be able to make rational decisions based on measurement and fact-based analysis in adherence to the precept, "In God, trust. All others bring data." Attributed to W. Edwards Deming and others. Definitions. There are many different definitions of quality. For some it is the capability of a software product to conform to requirements, while for others it can be synonymous with customer value, or even defect level. The first definition of quality history remembers is from Schohart in the beginning of 20th century. There are two common aspects of quality. One of them has to do with the consideration of the quality of a thing as an objective reality independent of the existence of man. The other has to do with what we think, feel or sense as a result of the objective reality. In other words, there is a subjective side of quality. Kitchenham, Flieger, and Garvin's 5 Perspectives on Quality. Kitchenham and Flieger, further reporting the teachings of David Garvin, identify 5 different perspectives on quality. The Transcendental Perspective deals with the metaphysical aspect of quality. In this view of quality, it is something toward which we strive as an ideal, but may never implement completely. It can hardly be defined, but is similar to what a federal judge once commented about obscenity. "I know it when I see it." The user perspective is concerned with the appropriateness of the product for a given context of use, whereas the transcendental view is ethereal. The user view is more concrete, grounded in the product characteristics that meet users' needs. The manufacturing perspective represents quality as conformance to requirements. This aspect of quality is stressed by standards such as ISO 9001, which defines quality as the degree to which a set of inherent characteristics fulfills requirements. The product perspective implies that quality can be appreciated by measuring the inherent characteristics of the product. The final perspective of quality is value-based. This perspective recognizes that the different perspectives of quality may have different importance, or value, to various stakeholders. Software quality. According to Deming, the problem inherent in attempts to define the quality of a product, almost any product, were stated by the master Walter A. Schohart. The difficulty in defining quality is to translate future needs of the user into measurable characteristics, so that a product can be designed and turned out to give satisfaction at a price that the user will pay. This is not easy, and as soon as one feels fairly successful in the endeavor, he finds that the needs of the consumer have changed. competitors have moved in, etc. Software quality. According to Feigenbaum, quality is a customer determination, not an engineer's determination, not a marketing determination, nor a general management determination. It is based on the customer's actual experience with the product or service, measured against his or her requirements, stated or unstated, conscious or merely sensed, technically operational or entirely subjective, and always representing a moving target in a competitive market. Software quality. According to Juran, the word quality has multiple meanings. Two of these meanings dominate the use of the word. 1. Quality consists of those product features which meet the need of customers and thereby provide product satisfaction. 2. Quality consists of freedom from deficiencies. Nevertheless, in a handbook such as this, it is convenient to standardize on a short definition of the word quality as fitness for use. CISQ's quality model. Even though quality is a perceptual, conditional and somewhat subjective attribute and may be understood differently by different people, software structural quality characteristics have been clearly defined by the Consortium for IT Software Quality, under the guidance of Bill Curtis, co-author of the Capability Maturity Model Framework and CISQ's first director, and Capers-Jones, CISQ's distinguished advisor. CISQ has defined 5 major desirable characteristics of a piece of software needed to provide business value. In the House of Quality model, these are what's that need to be achieved: reliability, an attribute of resiliency and structural solidity. Reliability measures the level of risk and the likelihood of potential application failures. It also measures the defects injected due to modifications made to the software. The goal for checking and monitoring reliability is to reduce and prevent application downtime, application outages and errors that directly affect users, and enhance the image of IT and its impact on a company's business performance. Efficiency. The source code and software architecture attributes are the elements that ensure high performance once the application is in runtime mode. Efficiency is especially important for applications in high execution speed environments such as algorithmic or transactional processing, where performance and scalability are paramount. An analysis of source code efficiency and scalability provides a clear picture of the latent business risks and the harm they can cause to customer satisfaction due to response time degradation. Security. A measure of the likelihood of potential security breaches due to poor coding practices and architecture. This quantifies the risk of encountering critical vulnerabilities that damage the business. Maintainability. Maintainability includes the notion of adaptability, portability and transferability. Measuring and monitoring maintainability is a must for mission-critical applications where change is driven by tight time-to-market schedules and where it is important for IT to remain responsive to business-driven changes. It is also essential to keep maintenance costs under control. Size. While not a quality attribute, per se, the sizing of source code is a software characteristic that obviously impacts maintainability. Combined with the above quality characteristics, software size can be used to assess the amount of work produced and to be done by teams, as well as their productivity through correlation with timesheet data, and other SDLC-related metrics. Software functional quality is defined as conformance to explicitly stated functional requirements, identified for example using voice of the customer analysis and the level of satisfaction experienced by end users. The latter is referred to as usability and is concerned with how intuitive and responsive the user interface is, how easily simple and complex operations can be performed, and how useful error messages are. Typically, software testing practices and tools ensure that a piece of software behaves in compliance with the original design, planned user experience and desired testability, i.e., a piece of software's disposition to support acceptance criteria. The dual structural, functional dimension of software quality is consistent with the model proposed in Steve McConnell's Code Complete, which divides software characteristics into two pieces: internal and external quality characteristics. External quality characteristics are those parts of a product that face its users, where internal quality characteristics are those that do not. Alternative approaches. One of the challenges in defining quality is that everyone feels they understand it, and other definitions of software quality could be based on extending the various descriptions of the concept of quality used in business. Dr. Tom DeMarco has proposed that a product's quality is a function of how much it changes the world for the better. This can be interpreted as meaning that functional quality and user satisfaction are more important than structural quality in determining software quality. Another definition, coined by Gerald Weinberg in Quality Software Management Systems Thinking, is quality as value to some person. This definition stresses that quality is inherently subjective. Different people will experience the quality of the same software differently. One strength of this definition is the questions it invites software teams to consider, such as, who are the people we want to value our software, and what will be valuable to them?